Welcome to Plutus IES, and today we are covering the topic Valence Bond Theory uh, from the unit Coordination Chemistry that covers your paper 1 of the UPSC chemistry optional syllabus. Now, in case of Valence VBT theory, it utilizes the similar concept that it has used in chemical bonding, describing the bonding pattern between carbon and other elements using the covalent bonding, and utilize that same concept in your coordination compound. So it states, just like in case of covalent bonding, it is also treating coordinate bond as a special case for your covalent bonding. So it suggests, just like covalent bonding to happen, the covalent bonding occurs as the element of as the ligands or the donors with excess electron density overlaps over the empty orbitals of the metal. Now, the general electronic configuration for the d block elements is given by n-1d and ns2. Then we have other orbitals which are np and nd. It states, when the ligand approaches the metal center, based on whatever the number of ligands that are approaching the metal center for a definite type of complex formation, based on that, the metal can arrange whatever the electrons it has into a definite arrangement so that it can receive the electron density from the ligands. Now, based on whether the ligand carries excess amount of electron density or is too much electronegative in nature, we say that the ligand will act as a strong field ligand and can cause pairing of electrons in the orbitals. If the pairing of electrons is being considered is happening, we'll see that the ligand that has approached the complex metal center is called as a strong field ligand, and if it cannot lead to the pairing of electrons, that means the electron remains unpaired, it will be called as a weak ligand. Now, the thing is that VBT, for most of the cases, the theory is not actually applicable. Why? Because for to use a VBT to explain the structure of a given compound, you need to know the number of unpaired electrons, which is you need to know about the magnetic spin only moment. But as soon as we know the number of unpaired electron that we have, we can tell how the ligand is acting as a strong field or a weak field, and based on what is the total number of ligands that I have approached and how many numbers of electrons are paired or unpaired, we can also determine the geometry of the complex. So VBT decides everything solely on the basis of number of unpaired electron it has. And if we already have them, then there is no need of VBT. So what does it actually state? So it states, if in case your ligand is having electrons ranging from 1 to 3, for formation of any complex it requires electrons. Now, for the formation of octahedral complex, it requires D2 sp3 hybridization. It requires at least of 2d orbitals. So in case still of D3, you can always get two empty orbitals of d, one empty s orbital and 3p orbital, which can give you d2sp3. In such case scenario, since we are using the inner orbital, these complexes called as inner orbital complex. But remember, the inner orbital complex are not for D3, they are defined when you are going for a D4 type or T5 type complex when you do not have enough space. So for that, if the ligand is a strong field ligand, that it might cause pairing of the electrons, creating space for utilization of these D2 orbitals. If this is occurring, then you can only call it inner orbital complex. That means for the case of D4 and D5 low spin cases. D4, D5 low spin cases. If the ligand is a weak ligand, it cannot pair the electrons. In such scenarios, we need to utilize the outer 2d orbitals, and this will be give you hybridization sp3d2. And these complexes will be called as outer orbital complex, or you will call them high spin complex. They will be called as your low spin complex. Now, the thing is, even though it can define how the geometry of a particular complex is being attained using the concept of hybridization, it fails to define the structure of the complex or geometry in cases like involving D5 series of elements, having copper complexes, okay, and in case of nickel C4 type. It cannot make exact predictions regarding the coordination number 4, whether they are tetrahedral or they are square planar. For that to know, we can only decide based on the value of the magnetic moment we have. But if we have the magnetic moment, then there is no need of VBT. So the thing is, these two complexes are square planar, but if you go by VBT's general theory, it should come out to be sp3, which is entirely wrong. It is actually square planar. Why? Because this is a extreme case of GTD of D9 configuration, which convert an octahedral complex into a square planar complex, while we need to this is can only be explained in terms of CFT only, that it is the metal center which is responsible for formation of this complex into square planar, and here we need to take into account the effect of the ligands. So these are the major problems that VBT could not define. It took number of observation which it cannot explain. It cannot explain when to take a ligand as a strong, when to take ligand as a weak. It cannot explain complex the color exhibited by the compounds. It cannot make exact predictions regarding the coordination number 4 complexes. So here the thing is, all in all, we need to remember that VBT is very much useless. Apart from giving you an idea of regarding the hybridization of complex, especially in case of coordination number 6, it is useless for other cases because it can only be derived based on the magnetic moment value, and if we have that, there is no need for VBT. So I hope this would have cleared all of your doubt and you have learned something. In case of any doubts, you can add it to the comment section and we'll get back to you. Thank you for joining us.